All right, welcome back. So today we'll be talking about combinations of capacitors. Um, so quickly, last time we talked about capacitors. So basically, you have two plates next to each other. Then you have a capacitor. You can store both charge and energy. So capacitance of a capacitor is equal to um, the charge on the plate divided by the voltage across the two plates. And for parallel plate capacitors, um, so the capacitance is just proportional to the area of the plates, and then the inversely proportional to the distance, with this constant number here, which is the permittivity of free space. And if you have insulator in between the two plates, then you actually can um, increase the capacitance by a factor of kappa, which kappa is equal to it's called the dielectric constant of the insulators. Okay. The energy stored in the capacitor is equal to 1/2 of the charge you store times the voltage across two plates, or equal to 1/2 the capacitance times the voltage square, or the charge square over 2 times capacitance, depending on what you know of. You can pick and choose one, two equation of the expression to calculate for the energy. Today we'll be looking at if you have multiple capacitors in the circuits, then what will be the total capacitance of the combination? We call it equivalent capacitance. Okay, so let's take a look on when you have with the simple configuration, when you have just two capacitors, they are parallel to each other. So there's one here, and then parallel to that one is another one here. So each capacitor is made of two plates, metal plates. Okay, and in the circuit, this is what you're going to see in the circuit. If you have capacitors, you're going to use two equal length lines parallel to each other, look like very similar to battery signs that we'll see later on. For battery, it's two lines also, but one is shorter than the other one. But for capacitors, they are the same. Okay, so you see that. And then this will be the second capacitor. So if they are parallel to each other, then they share the same voltage. So when you see the terms, if two elements are parallel to each other, that means they share the same voltage across, okay, the terminals. And when you see the term when it says they are in series, that means they share the same current or charge. Okay, so in that case. So we can calculate for the charge on this guy because they share the same voltage. So we'll just say V across the two. The same thing will be the difference between these 2 points. So the same V. So on first capacitor, the plates here, the charges will be C1 V1 times V. On the second capacitor, the charges on the two plate will be Q2, which is C2 times V. Okay. So now the combination, we can treat the combination as just one single capacitor, then we call it equivalent capacitance of the capacitor, okay? So then we can take a look at the total charge on the combination, which is Q1 plus Q2, which is equal C1V plus C2V, or C1 plus C2V. And that will equal to a C equivalent times the V. So in that sense, it's easy to see that the equivalent then will be just C1 plus C2 when the two are in parallel to each other. Okay. So for the capacitors in parallel, their equivalent capacitance will be the sum of the two. Now, if you have three or more, then you just add the third one and the extra ones up. Okay, so if you have three, then it'll be C1 plus C2 plus C3. Okay, so you can draw a figure here again. This is a battery, as I mentioned earlier. So longer line, a shorter line, and then longer line is the positive terminal, short line represent the negative terminal in that case. And then this CEQ means it's the representation of these two in parallel. Okay, so in that case, if you have three, you add three up. Okay, if you have more than three, you add the rest up. Okay, so that's the equivalent capacitance for capacitors in parallel. Now let's take a look on a simple example here. So it says you have uh, two capacitors in parallel. What's the equivalent? Okay, so simply we will just add them up, right? So in this case, we'll just say CEQ then should be just equal to C2 plus C1 plus C2, which is then 36 microfarad plus 18 microfarad, and simply that will give you 54 just microfarad. Okay, so that will be that one. Okay, so this is an easy example. All right, now let's take a look on if the capacitors are in series, so that means they are connected one after another. So in series, they will share current or charge in the case that if there's no current. So in this case, they are sharing the charge. So when you have those three in series, so then if you charge the combination, then this guy will get plus Q. So plus Q flow out of the positive terminal, negative Q flows out of the negative terminal. So this guy will get minus Q. And because there's plus Q here, on the other side, this will be minus Q. And if you have minus Q here, this will be plus Q because there's no charge going through the plate. It's they are separated. Okay, so if you on this wire, if you get minus Q on this guy will be positive Q. Okay, and then the same here, this guy get minus Q, this guy get positive Q. Okay, so the total net charge on each wire should be still be 0 in a sense, but um, if you have them in series, so then equivalent, the combination can be represented by this equivalent capacitor. Okay, so in that sense, if they are in series, they share the same charge, but we can take a look at the voltage here. So this guy will be V1 here. So let's say V1 here, V1. That should be equal to the Q over C1. Okay. And then on this one, V2 is going to be equal to the Q over C2. On this guy, V3 is going to be Q over C3. But they are one after another, so the voltage V1, V2, V3 should add up to be the total voltage. Okay, so V1 plus V2 plus V3, then should be equal to the total voltage of the battery. Okay, which in this case, the total voltage you can see from the equivalent circuit here, that should be equal to C times CEQ, okay? Because C is equal to the voltage or the Q divided by the voltage. So the voltage then, well, actually, give me 1 second. So, that's not quite right there. Let's see, and erase. So let's do from the beginning here. V1 is Q over C1. V2 is Q over C2. V3 is Q over C3. On here, epsilon is equal to Q over CEQ. Okay, so my bad there, because C is equal to Q over voltage. Okay, so then V1 plus V2 plus V3 should be equal to epsilon, which means Q over C1 plus Q over C2 plus Q over C3 should be equal to Q over CEQ. Okay, so you'll see that Q will actually cancel across. Okay, so then 1 over C1 plus 1 over C2 plus 1 over C3 should be equal to 1 over CEQ. Okay, so that's the relationship. So your equivalent capacitance should be, or inverse of your equivalent capacitance should be equal to inverse of each of those individual one add up. Okay. All right. So the conclusion, if you have capacitors in series, you do inverse of each one and add them up, that equal to the inverse of the equivalent. So then to calculate for your equivalent, right, you need to do inverse. Okay, so your CEQ then it should be equal to 1 over C1 plus 1 over C2 plus 1 over C3. Let's see. All right. So CEQ should be equal to all this, like inverse. Okay, so we can do that if we are looking just for CEQ. Okay, all right. Let's take a look on this example. So this one says you have 2.52 microfarad capacitor connected with a 126 in series. What's the CEQ? Okay, so this one, think again, once we identify it's in series, we can use that equation. So then CEQ in this case is equal to 1 over C1 plus 1 over C2, and then we'll inverse. Okay, so remember to do that. 1 over 252 plus 1 over 126, okay? And then inverse of that. That will give you the equivalent to be 84, and that should be in micro farad, okay? So this is when they are in series. So you do inverse of each other, add up, and then inverse again, okay? To get that. Now, in reality, they might not always just be purely in parallel or in series, right? There's will be some part in parallel and some part maybe in series, and then with combination, maybe with more complicated combination, okay? So then what to do is you are going to look at the simplest combination first, identify if it's in parallel or in series, and then you tackle that part first, and then after that, look at that part to another capacitor or maybe another combination of capacitor, and then see if they are in parallel or in series. So let's take a look on this one, okay? So in here, these two are in a line, so they are one after another, okay? So these two are in series. And so this is where the voltage will be applied. Okay, so the combination of these two then will be in parallel with this guy. Okay, so these two are in series, and then this combination is with um, in parallel with this one. So we'll do these two first. Okay, now in series. So then CEQ of that part should be 1 over 8.2 plus 1 over 22, and then we'll inverse that. Okay. So that will give us, for this first part, I guess I did not calculate, but you guys can calculate this, okay? Or maybe let me just do a quick calculation and then I'll tell you what that is, okay? 8.2 plus 1 over 22 and back, okay? 1 over 8.2 plus 1 over 22, and then inverse of that. Okay, inverse of that. Okay, so that gives me about 5 5.98, 5.97. Okay, 5.97 microfarad. Okay, so then this is replaced by a single this guy is replaced by a single 5.97. So now the circuit becomes 15 microfarad in parallel with 5.97 microfarad. Okay, so now it's just this one and this one in parallel. Now, when they're in parallel, so then the equivalent of this guy will be the two add up. Okay, so the final CEQ, let me call it prime, then it should be just 15 plus 5.97, which give me about just 21 micro farad on that. Okay, so this will be the solution to this guy. Okay, so we treat this one first, and then this one will be in parallel with that part. Okay, all right. Next, let's take a look on disconnected and reconnected capacitors. Okay, so capacitors they restore or they store energy and charge, and what we want to do with is later on we will actually get the charge out. Okay, so a lot of times it happens you charge it and then discharge it. Okay, so let's see what this one is about. So this one says you have 100 PF for picofarad capacitor and a 400 picofarad capacitor are both charged to 2.00 kilovolts. They are then disconnected from the voltage source and are connected together. In this case, just positive plate to the negative plate and negative plate to positive plate. Find the resulting potential across each capacitor. Okay. So they are both charged to the same voltage. That means they are in parallel initially. Okay, so we can take a look on this one here. Where's this guy here? All right. And let's draw the original combination here. So C1, capacitor 1, okay, we call it C1. And then there's a capacitor 2, call it C2. So both are connected to the same terminal here. So across these two terminal plus and minus here is 2 kilovolts. Okay, so right here, this is plus on this end, that's minus on that. So across this plus and minus 2 kilovolts. This is original combination. So let's see here. So what happens is when this is charged, right, you'll get positive Q on the top here, and then negative Q there, Q1. On this one, you get positive Q2. On this guy, you get negative Q2 at the bottom plate, okay? So now it says what happens next is you actually disconnect both of them from the source, and then you're connecting the top plate of 1 to the bottom plate, and then the top plate of 2 to the bottom plate of 1. Okay, so kind of like that, but it's a little bit messy there. So let's just reorganize things. So it becomes now we'll keep this one here, C1 here. So we'll still have positive Q1 and negative Q1 here. Now on the other side here, we actually will flip the two. Okay. So then we'll have minus Q2 on top, but positive Q2 at the bottom. So this is our C2 here. Now we connect them together. It's asking you then what will be, now I'm not sure if this will be positive. So let's just erase that positive sign there. Now what will be the voltage across this guy and this guy? Okay. So now the new voltage across this and this. Okay. So now we can see that positive Q1 and negative Q2 they're connected together. So charge will partially cancel, right? Because positive and negative will cancel partially. And then on here, it will also cancel. So the question is, which one has bigger magnitude, Q1 or Q2, right? We can calculate that and then we will see if we will see what's the case. Let's do that first, okay? So Q1 is C1 times V initially given. So then 100 pico 10 to the negative 12, 10 to the negative 12, F times 2K V. So that gives us 200 times 10 to the minus 9 coulombs. Okay. Q2, we can do the same thing, C2 times V, which is 400 pico times, again, 2 kilo. That will be 800 times 10 to the minus 9 coulomb. Okay, so clearly Q2 is more than Q1. So then at the end, when these two, positive Q1 and negative Q2, they combine, you will get then minus, right? Minus of Q2 minus Q1. And on the other end, you'll get positive of Q2 minus Q1 there. Okay. So, and these two are still parallel to each other, so we can calculate what will be the total charge, and then we can do, because they are combined, right? So the equivalent, we can calculate equivalent, CEQ of the combined should be the two add up, right? Parallel, so C1 plus C2, and that will give us just 500 picofarad. The Q total will be now actually Q2 minus Q1. Okay, so the 800 minus the 200, that will be 600, 10 to the minus 9 coulombs. Okay, so this is charge. This is that CEQ. So then we can calculate V. V then will be equal to Q total over CEQ. So that will be the 600 10 to the minus 9 over the 500 10 to the minus 12. Okay, so that gives us 200 volts. So at the end, you'll get that. Okay, much of charge there. Okay, all right. So let's go back to the slide. Loading. Okay. And we'll stop there. So this is what we learned today, combination of capacitors. You can use equivalent capacitor to represent the combinations. If they are purely in series, you do inverse of each and add up and then do the inverse to get the equivalent. If they are in parallel, you just add them up. If they are in complete combinations, you'll treat the simplest combination first, just the ones purely in series or in parallel first, and then look at the next section, this combination with another element or another combination, and doing so on and so forth. In order, for to the end, we will get either just equivalent with another one to be in series or in parallel, and that will be it. Okay. And we also talk about charge and discharge capacitors, but that will be it for today. We'll see you guys in a I'll see you guys in a next lecture.